So in section 3.1, we are now going to use the concept of limits that you just took a test on in order to build up to a more important concept that's going to take us all the way through calculus. Right? This is one of two things that I would say are the single most important things. Derivatives, and the other one is antiderivatives, so as you imagine, they're linked. All right? So in 3.1, tangents and the derivative at a point. So I've teased you with this before. The slope of the curve, right? We know that the slope of the curve was the same thing as the slope of a tangent line, right? Now, remember that we said the slope of the tangent line was, in a way, a limiting value of the slopes of secant lines, right? And the difference quotient represented the slope of secant lines. So now we actually apply this limit now that we have this concept. The slope of the tangent line, and hence the slope of a curve itself, is the limit as h approaches 0 of the difference quotient. All right? Now, for the moment, this is being defined as the derivative at a point. So this x sub 0 represents a specific x, at least for the moment. Now, if we jump into the exercises and take a look at a graph. Number 2, for example. So here we have a graph with 2 points P1 and P2, and they're asking us to make a rough estimate of the slope of the curve. So what I'm going to do is I'm actually going to draw the tangent line. We know the tangent line does what? It touches that curve just once at that moment parallel, right? So if I look at actually P2 up here, it looks like that's at the top of that curve. So what would the tangent line look like there, do you think? Do you think the tangent line would be a horizontal line? Does that seem reasonable? But what is the slope? The slope of a horizontal line is 0. So what is the slope of the curve at P2? We'd say it's 0, right? Now if I look at P1, right, this one's a little trickier, and they did say make a rough estimate, so, you know, blind as I am, this is going to be pretty rough. Let's say, that's pretty bad. That's about as good as it's going to get. So here's the tangent line that's touching the curve at P1, right? Now just making a rough estimate, what would you say the slope of that tangent line is? So it looks like I've hit these 2 points where I fall 2 and run 1. So -2 for the slope. I mean, if you decide that it just looks like -2.11 to you, I'm not going to argue that. All right? That's a rough estimate. So the slope of the curve at P1 is -2. Now, lines have constant slopes, right? It's the same slope all the way along the line. Curves have slopes that change at any given point, and that's what that definition we have will allow us to find. All right? So with just a single point, we can find the slope of the tangent line. We don't need 2 points for a slope of these lines. So let's say that we're asked to find the slope of y equals x minus 1 over x plus 1 at the x value of 0. All right? So according to the definition, the slope, m, is the limit as h approaches 0 of the difference quotient, right? Only in this case, what is x? So it's limit as h approaches 0 of f of 0 plus h minus f of 0 over h. Do you see how I set up that definition? So the limit as h approaches 0. Now 0 plus h is just h. All right, pause there, was not good for my heart. So f of h is h minus 1 over h plus 1 minus, what is f of 0? Wouldn't it be negative 1? If I plug in 0 for x, minus 1 over plus 1 is negative 1 all over h. So the limit as h approaches 0. H minus 1 over h plus 1 all over h. All right, now we've practiced evaluating limits like this. If I tried direct substitution, I'd wind up with 0 over 0, which is indeterminate. So what would I need to do? So the LCD is what? H plus 1. And we multiply the top and the bottom of the main fraction bar. So I have the limit as h approaches 0. That's now going to be just h minus 1 plus h plus 1 times 1 over h times h plus 1. And what happens in the top? The ones cancel. We have 2h over h plus 1. Now what happens? One of the h's cancels. And finally, at this step, we are now able to evaluate the limit. If I use direct substitution, I get 2 over 0 plus 1, which is 2. So what is the slope of this rational function at 0? 2. That's a positive value, right? And what did positive slopes tell you? Increasing, right? What if I ask you to find the tangent line of f of x equals square root of x plus 1 at 8, 3. Now, of course, that point should be on the graph. So if you plug in 8, the answer should be 3. Otherwise, something went wrong. All right? So traditionally, you needed a point and a slope to get the equation of a line, right? Do we have a point? Yeah, that one kind of slaps you in the face, right? What about slope? We now have a way to find slope with just one point. So tell me the definition. Hint, it starts with limit. Limit as h approaches 0, what? All right, so in this case, x is 8. So that's going to be f of 8 plus h minus f of 8 all over h. So now we have the limit as h approaches 0. Square root of, what is f of 8 plus h? Square root of, I mean, you just have to read it, guys. Throw me a bone. Then we have minus f of 8, which is square root of 8 plus 1, all over h. So we have the limit as h approaches 0. And I warned you on the last test, and that has not gone away. Do not drop your limit, right? Until you've actually evaluated it, that limit notation is required to be there or your answer is wrong. All right? So that's going to be the square root of 9 plus h, right? What about the second one? Just 3. So minus 3 all over h. All right, again, direct substitution is not going to work. It gives us an indeterminate form. Go ahead and do it now. What is it that I need? All right, there you go. We want the conjugate. Multiply the top and bottom by square root of 9 plus h plus 3. So I have the limit as h approaches 0. And up top, that's going to be a difference of squares. So that's 9 plus h minus 9, right? On the bottom, we're just going to multiply it in and not through. Just put it there. H times square root of 9 plus h plus 3. Unsurprisingly, what happens? 9 minus 9 cancels out, so you're just left with an h, right? Over an h. So it's going to reduce. So I'm going to be left with 1 over square root of 9 plus h plus 3. You guys okay with that? Can I use direct substitution now? So now I have 1 over square root of 9 plus 0 and then plus 3. Well, that's going to be 1 over 6. You guys agree? All right, so the slope of the curve, square root of x plus 1 at 8, 3, the slope is 1/6, positive, right? And a positive slope means it's increasing there, right? If you think back to your algebra, you should be able to picture a square root in your mind's eye, right, what the graph looks like. But that's not what this one was just asking for. The slope was just one step. Now it wants the tangent line. So where do we go from there? You got it. So for the tangent line, y minus y1 equals m times x minus x1, where we need a point and a slope, and we have it. The point was 8, 3. The slope was 1/6. So this is y minus 3 equals 1/6 times x minus 8. If I distribute the 1/6 and then add 3, I get y equals 1/6x, and then that's going to be plus 5/3. Flying solo up here, apparently. So this represents the tangent line. Now what should the tangent line do? What is this line we just found? It's going to graze our graph, touching just at that point, at that moment in time, parallel, and then they part, never to meet again. Okay. Now, there is something out there. You won't really do much with it until Calc 3, but just know that it's out there. Something called the normal line. Now, I already baked your noodles in trig when I told you that two vectors that meet at 90 degrees are described as what? Orthogonal, right? When two lines meet at 90 degrees, we call it perpendicular. I was hoping you guys would have that one. Okay. And then if two planes, or a line and a plane, meet at 90 degrees, we call it normal. So normal is the same as orthogonal, is the same as perpendicular. It just means two things are meeting at 90 degrees. So rather than at that moment in time that they touch their parallel, the normal line at that moment in time is perpendicular, crossing at 90 degrees at that instant in time. Now, Thinking back to how perpendicular lines work, if our slope is 1/6, what would the perpendicular slope be? -6/1, which is -6. Ah, everything you learned comes back. You escape nothing. Nothing. The ghost from Christmas past is just on your butt. All right? So we've got y minus 3 equals -6. Opposite reciprocal for perpendicular times x minus 8. So y minus 3 is -6x plus 48. So y equals -6x plus 51. Now why don't we just graph what we've done so we can visually see what it is that we have actually accomplished. So I'll go to y equals, and I'll actually plug in the function itself, which was square root of x plus 1. Then for my second one, I'm going to plug in y equals 1/6x plus 5/3, right? And then for the third one, I'm going to plug in y equals -6x plus 51. Is that all right? Now, before I graph it, I'm actually going to go to zoom, and I'm going to do zoom square, right, just so that we see it a little bit more clearly. Actually, let me change my window first. So I'm going to go from 0 to 10 instead of -10 to 10 for both of these. Let's see what it looks like. And then zoom square. So here's my function. Here is the tangent line. There is the normal line. So at that moment, 8,3 on the curve, the tangent line is just grazing it parallel, while the normal line is cutting through it at a 90-degree angle. Is that okay? Looks like we put a target on that point, a crosshair. All right. Now, the derivative represents a rate of change, which we're going to spend all of your next test pretty much discussing the applications of. But let's just take a peek at some applications of it for now. So let's look at number 32. What is the rate of change of the volume of a ball? And it tells you that the volume of a ball is 4/3 pi r cubed. Right? Some of you guys heard of that before? What is the rate of change of volume with respect to the radius when the radius is 2? So let's assume that we're blowing this ball up, right, like a balloon. And as that balloon gets bigger, its radius is getting bigger, so its volume is getting bigger, right? This is asking us the rate of change. So, I'm going to introduce a notation here. We have v equals 4/3 pi r cubed. V prime of 2. So this prime mark is letting me know that I'm looking at the derivative. All right? And they're asking for it at r equals 2.
Is that like a comma or?
You could think of it as an apostrophe, sort of. It's a prime mark. So we have the limit as h approaches 0, And it's f of x plus h minus f of x all over h, right? So what is x in this case? R, right? Which is 2. So 2 plus h. And I guess I could call it v. V of 2 plus h minus v of 2 all over h. We could say that f of r equals v. This is fine. So we just set up our definition for the derivative at this point. So the limit is h approaches 0. And what is v of 2 plus h? Four thirds pi 2 plus h cubed, right? Minus, and then v of 2, that's 4 thirds pi 2 cubed all over h. Let me see some neck action. You guys with me on the setup?
Do we have to bring E prime over? Like we have to bring the limits over?
No, this is naming it. So the whole limit is named this v prime notation. All right. I'm stealing from the next section just for ease of writing this. All right. Now, we need to evaluate this. Both of the numerator terms have 4 thirds pi, right? So I can bring it out front. 4 thirds pi, limit as h approaches 0. And then that would be 2 plus h cubed minus 8 all over h. You guys agree? That was one of our limit properties. If we have a constant multiple, it just comes along for the ride. And if it just comes along for the ride, we can put it out front. All right. So you have 4 thirds pi, limit as h approaches 0. And we multiply out this cube, right? So do you guys remember how to do that, since we did it on day 1 with algebra review? It's your binomial expansion, right? Oh, snap. Right? I didn't waste your time. It pops up. So your coefficients, just to remind you, we're going to do second stat, which is your list menu. I'm going to go over to sequence under ops. My expression is going to be 3 choose x, so 3 math PRB, combination x. My variable is x, and I'm going to count from 0 to 3 by ones. Now, some of you guys have expanded a cube enough that you remember 1, 3, 3, 1 are the coefficients. Is that all right? So in addition to those coefficients, we're going to start 2 off to the 3rd power and then drop it by 1. And we're going to start h off to the 0th power and raise it, right? So the first term is going to be 8. Times 1 times h to the 0 is still just 8. Plus, the next term is going to be 4 times 3 times h, which is 12h. Right? 2 squared is 4, and then there's that 3 from the binomial expansion's coefficients. Plus 2 to the first is 2 times a coefficient of 3. So that's going to be 6h squared. You guys agree? And then the last one's going to be 2 to the 0, which is 1. And that's going to be 1h cubed. Then we have minus 8, which stuck around all over h. So the 8 minus 8 will cancel, right? And everything that's left has an h in it, which therefore reduces. So I have 4 thirds pi, limit as h approaches 0, and this is going to wind up being 12 plus 6h plus h squared. Are you guys with me on that? I reduced by that common denominator of h. Now can I use direct substitution? So it's 4/3 pi times 12 plus 0 plus 0, if I plug in 0 for h, which winds up being 16 pi. Now, geometrically, this is the slope of the curve, which is positive, which means increasing. In terms of the physical application, what is the volume of this ball doing? It is increasing. Let's do one more of those. Let's look at number 30. If balls don't excite you, maybe a rocket will. At t seconds after liftoff, the height of a rocket is 3t squared feet. How fast is the rocket climbing 10 seconds after takeoff? All right, so they gave us a function. Right? I could call it a of t for altitude. And a of t was 3t squared. So they want me to find the rate of change, which is our hint that we're looking at the derivative when we are 10 seconds past liftoff, right? So that would be a prime of 10. All right?
How do we know when we're supposed to use the A prime or whatever, the prime thing?
Anytime they're talking about a rate of change, that is derivative. All right? We're just dipping our toes in for the moment. We're going to have a whole lot of time spent on that later. All right? Just giving you two applications for now to tide you over. So, most importantly in this section, the definition, limit, as h approaches 0 of a of 10 plus h minus a of 10 all over h. Do you guys see how I'm setting this up? So we've got the limit as h approaches 0. That's going to be 3 times 10 plus h squared minus 3 times 10 squared all over h. You guys agree? I could pull a 3 out front. It's not as bad as a fraction, but if you're so inclined, you can pull it out front. Limit as h approaches 0, so then that's going to be (10 plus h squared minus 100 all over h). Let's multiply it out. At least I gave you a square this time instead of a cube. So you have 3 times the limit as h approaches 0, and tell me what to write for my numerator. I'm assuming you guys can do a square. 100 plus 20h plus h squared, and then we still carry over the minus 100 over h. We've already seen the difference quotient, so this doesn't shock us. The hundreds cancel. Everything that's left has an h in it, which we can therefore reduce. So I'm going to have 3 times the limit as h approaches 0, and that's going to be 20 plus h, and that's it. So now I can evaluate using direct substitution. 3 times 20 plus 0, what is it? 60. I think they gave us units here. So this would be feet per second. It's feet per second. So 10 seconds after liftoff, the rocket is moving at 60 feet per second. Before that, it was probably moving a little bit slower. After that, it's probably moving a little bit faster. But at that moment in time, its rate of change, its instantaneous speed is 60 feet per second. All right. So let's move to our next section. All right. The good news is this chapter kind of starts off the worst and gets a little better as we go. Let's see if you guys think so. All right. So here we define the derivative. That's it. In the previous section, it was the derivative at a point. Now we're just saying the derivative. The derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. So what's different about this? In this, x is still a variable. It's not a number that we've plugged in yet. X is now representing a variable. So we're still going to use this f prime of x notation as one of our notations. All right? But we have a consequence here. So this is 3.2. The derivative as a function. All right? Now it's not just going to be a value. It's going to be a function. All right? Now, there are several different notations that are out there for the derivative as a function. One of the most basic ones, f prime of x, like we just saw in the definition. If it's using y, you can use y prime. That's that prime mark still. We also have Leibniz notation. Leibniz was a German mathematician who concurrently developed calculus alongside Newton and battled for years afterwards over who got credit. All right? His notation for the derivative is dy dx, which is how we read that. All right? And what's nice about Leibniz notation is it tells you still what your dependent and independent variables are. Your dependent is y, your independent is x. All right? The f prime of x notation does a pretty good job of that too. Y prime is missing that information, so it's a little bit more casual. All right? You can see df dx, ddx of f of x, and then even using capital D to represent a derivative operator. All right? Pretty much outside of AP high school calculus, we're not going to see the capital D notation. Not here. All right? Mostly f prime of x, y prime, dy dx, or df dx, that Leibniz notation. Okay, so what we're doing now is using that definition without plugging in an x first. So we're going to get a function. All right? The derivative is going to be a function. So let's say that I give you f of x equals x minus 1 squared and then plus 1. And I want to find the derivative of this function. All right? So I'll use the f prime of x notation for this one. F prime of x equals. And then the definition, the limit as h approaches 0, f of x plus h minus f of x all over h. So it's the limit as h approaches 0. This is going to be x plus h minus 1 squared plus 1. And I'll go ahead and put brackets just to emphasize that all of that is just the f of x plus h, right? Minus x minus 1 squared plus 1, that's f of x, all over h. You guys with me on this? Now, in order to do this, we need to multiply out this first square, right? But I'm going to show you a little trick, because in order to multiply that out, that's not FOILing, because it's 3 terms times 3 terms. So, I mean, there's a middle term. You might come up with some kind of like phemoimal that will get you there. All right. But what if I consider it x minus 1 plus h inside the square? Isn't that the same thing? What if I think of x minus 1 as a single term? All right. So we have the limit as h approaches 0. Now, squaring out a binomial is pretty easy. That's going to be x minus 1 squared plus 2h times x minus 1 plus h squared, right? A squared, ab doubled, b squared, right? Then we still have this plus 1 that comes along for the ride. Then I have minus, distribute the negative through the second set of brackets, minus x minus 1 squared minus 1. Right? Do you see how clever I was? I was very clever. Because what's going to happen? Yeah, x minus 1 squared minus x minus 1 squared cancels out. We didn't have to bother multiplying it out. It canceled, and now it's off our chest. Plus 1 minus 1 also cancels. So the only terms left, there are 2 terms left. They have h in it. We can reduce. So I have the limit as h approaches 0. That's going to be 2 times x minus 1, and then plus h. Are you guys with me on that? Can I use direct substitution now? Yes, I can. So 2 times x minus 1 plus 0 is simply 2 times x minus 1. Right? If you are so inclined, that's 2x minus 2. Don't care. This is fine. In fact, factored form is generally a nicer form. All right? So let me just summarize what we did. F of x was x minus 1 squared plus 1. What is its derivative? F prime of x is 2 times x minus 1. What kind of graph is f? It's a parabola, right? Isn't f prime also a graph? What is f prime? A line. All right. Let's try another one. What if I give you w equals z plus square root of z? So here's a function. I want its derivative. All right. So this time, how about we use Leibniz notation? All right. So if I use Leibniz notation, it's going to be dw dz. And the order that you put that in matters. What is your dependent variable and what is your independent variable? Your dependent variable is w. Your independent variable is z. Because you can plug in for z and then w depends on that answer. Is that okay? Do you guys see how I adapted Leibniz notation for this? All right. I hope I'm saying his name right. I mean, he's dead for a long time, so I won't hurt his feelings. But, you know, I don't speak German. All right, so dw dz, the derivative, by definition, limit as h approaches 0 of w of z plus h minus w of z all over h. Do you guys see how I adapted that definition? All right. So we have the limit as h approaches 0, and let's see what we've got. That's going to be z plus h plus square root of z plus h minus z plus square root of z all over h. Do you guys agree? So limit as h approaches 0. All right. Not a whole lot of multiplying out to be done here. We just have z plus h plus square root of z plus h minus z minus square root of z all over h. It didn't clean up very nice, right? But something does happen here. We do get z minus z, which cancels out. We're all about the slaughter, right? So I have the limit as h approaches 0. There's an h plus square root of z plus h minus square root of z all over h. Now, this is slightly different from how we've seen it before, but you know what tool needs to be used here. The conjugate is the right answer. Give yourself a pat on the back. Okay. So what am I going to multiply by? Top and bottom by square root of z plus h plus square root of z, square root of z plus h plus square root of z on the bottom. All right. This means I get the limit as h approaches 0. Now, the conjugate multiplies straight through to the h, as is, plus, but how does it multiply to the back two terms? As z plus h minus z. A squared minus b squared. That's a difference of squares. You guys agree? And on the bottom, that's h times square root of z plus h plus square root of z. All right, once again, what happens here? Z minus z. This is like a war of attrition. Right? We are filing away at this piece by piece. Right? Z's cancel. So I have the limit as h approaches 0. Now normally I can reduce the h at this point, right? But we're going to have to do a slightly different take on it here. How many terms are left in my numerator? 2 terms. So I could put the first term over the denominator. Well, h square root of z plus h plus square root of z over h square root of z plus h plus square root of z is 1. Plus, and then if I just put h over the common denominator, the h's cancel, and you're left with 1 over square root of z plus h plus square root of z. Let me see some neck action from you guys. You see what happened here, right? So I have 2 terms in the numerator. If I put the first term over the denominator, it's just 1. Then I carry down this plus sign right here. And then if I put h over the common denominator, the h reduces, so it's 1 over the denominator without h in it. All right? See, neck action earns some good points. You guys over here? Can we do direct substitution? I mean, we hope so. That was a lot of work, right? So that's 1 plus 1 over square root of z plus 0 plus square root of z. That's 1 plus 1 over 2 root z. Root z plus root z is 2 root z. You guys agree? All right. So just to remind ourselves, our function was w equals z plus square root of z. What was its derivative? The derivative, which we used dw dz, was 1 plus 1 over 2 square root z. Let's try one more. Let's say v equals t minus 1 over t. Here's a function. I want its derivative. All right. So because I've already used the other two notations, I'll use just v prime for this one. So we have the limit as h approaches 0, v of t plus h minus v of t all over h. You guys agree?
Do you have to put v prime of h, or t, or is v prime okay?
Both of them are fine. One of them's the f prime of x notation. The other one's the y prime notation. Yeah. Right, just showing you they're all out there so you get used to seeing them. You don't freak out. There's even another one out there. It's a sort of limited notation used in physics, but they'll put a dot above the variable to represent the derivative. Right? Usually that's specifically with respect to time. Right? But we'll have time for physics later. So this would be the limit as h approaches 0 of, tell me what to write. T plus h minus 1 over t plus h minus t minus 1 over t all over h. You just kind of died off on me there, but I finished it. All right, so once again, there actually isn't a lot of cleanup on this first step. We have the limit as h approaches 0, t plus h minus 1 over t plus h minus t plus 1 over t all over h. Basically, I just distributed the negative through the back brackets. And what happens? We are able to cancel t minus t. So we have the limit as h approaches 0, h minus 1 over t plus h plus 1 over t all over h. What is my strategy here? LCD. It's a complex fraction, right? These algebra tools wind up showing up in the same places every time, so you guys get an intuition for when to use them. What is your LCD here? T plus h. Is everybody okay with that? You get the LCD by looking at the denominators within the complex fraction. So you have the limit as h approaches 0. And now we multiply top and bottom by the LCD. So this means I have h times t plus h. That first term, nothing canceled. Minus, what happens with the second term? That's just going to be t. Plus, what happens with the third term? That's going to be t plus h. And on the bottom, ht, t plus h. Just multiplies in on the bottom. All right, so let's multiply it out. We have the limit as h approaches 0. Well, let's do it this way. I'll think of my first term, and then I'll think of the other two grouped together, all right? Because something obviously happens. If I take my first term over the common denominator, that's going to give me 1. We all love 1. All right? Now, for the rest of that, isn't that going to be negative t plus h? So won't the t's cancel there? So now all we have is h over that common denominator. So we've got plus 1 over t plus h. All right. So t minus t canceled, so we just have our first term over the common denominator, and then we have that final h over the common denominator, leaves me with those two terms. Can I use direct substitution now? That's my goal. 1 plus 1 over t times t plus 0, which is 1 plus 1 over t squared. Is that okay? So our function, v equals t minus 1 over t, our derivative v prime, 1 plus 1 over t squared. Is that okay? Let's look at one more for the moment. Let's say y equals 8 over square root of x minus 2. And let's say that I ask you to find the tangent line at x equals 6. All right? Now, some of your homework may ask you to find it at various values. Right? Do you want to have to use the definition for every single number? The correct answer to that is no, unless you're insane. All right? So we find the derivative as a function, and then we can plug in as many x values as we want. So we use the definition once, and then we can find all the different derivatives we want at various values of x. All right? So dy dx would be the limit as h approaches 0. And then what is it going to be? Let's do 8 over square root x plus h minus 2 minus 8 over square root of x minus 2 all over h. You guys agree? So what is my key here? LCD first. The pressing concern for the moment is that we have a complex fraction. What is your LCD? Yep, square root of x plus h minus 2, square root of x minus 2. Right? Do not multiply those out together. It's not wrong, but it just makes a bigger mess. All right? Instead, what do we do with it? Multiply it to the top and bottom of the main fraction bar. So this means, for my first term, I'm going to wind up with 8 times square root of x minus 2. Then I have, for my second term, minus 8 square root of x plus h minus 2 all over h. All right, and then on the bottom, that h is going to take on, I don't need parentheses for this. Square root of x plus h minus 2, square root of x minus 2. Right, there's no plus or minus outside the roots, so it's all just multiplication. Okay, now I could factor the 8 out from the top, right? You guys agree? It's optional, but getting it out of the way is not a bad idea. So 8 times the limit as h approaches 0, square root of x minus 2, minus square root of x plus h minus 2, all over that crazy denominator. Now what's my tool? The conjugate. So what do I use? Square root of x minus 2 plus square root of x plus h minus 2. You guys agree? All right. Now, it looks like we're making a terrible mess in the denominator, but the good news is we're not doing it out. We're just going to tack it on and accept it. So we have 8 times the limit as h approaches 0, and in the bottom, that's an h, square root of x plus h minus 2, square root of x minus 2, now parentheses, square root of x minus 2 plus square root of x plus h minus 2. It's just, adding on more factors each time. But it'll take care of itself very quickly. What about the numerator? X minus 2 minus x plus h minus 2. Now, I don't really want to rewrite that whole denominator just for the next step. So let's note that the numerator is x minus 2 minus x minus h plus 2. Would you guys agree? In which case, x minus x and negative 2 plus 2 all cancels out. So in fact, the only thing left in the numerator is a negative h, which is going to reduce with the h in the denominator. So I have limit as h approaches 0. Then I would have negative 1 with the h canceling, right? So I'm going to take that 8 out front and put it back. All right? It's optional, but I did it. Over square root x plus h minus 2, square root x minus 2, parentheses square root of x minus 2 plus square root of x plus h minus 2. You guys with me on this? Is this all right? I know it's not fun. Nobody said it would be. All right. But what can I do now? I can use direct substitution. So now I have just negative 8. That's now going to be square root of x plus 0 minus 2, square root of x minus 2, parentheses, square root of x minus 2, plus square root of x plus 0 minus 2. Now if I drop the zeros, I have a whole bunch of square roots of x minus 2. Right? So on the outside of the parentheses, square root of x minus 2 times square root of x minus 2 is x minus 2. Inside the parentheses, square root of x minus 2 plus square root of x minus 2 is 2 square root of x minus 2. What do you see? The 2 will reduce with the 8. So I just have a negative 4 up top. You guys agree? And then if I have x minus 2, square root of x minus 2, that's x minus 2 to the 3 halves in the denominator. I'm telling you, not a single shred of algebra will you escape. Right? Nor trig. But I haven't even thrown trig at your face yet. Right? It's coming. So this is our simplified derivative. Whew. So what is the derivative of y equals 8 over the square root of x minus 2? dy dx is negative 4 over x minus 2 to the 3 halves power. Now what was this question asking for? The equation of the tangent line. So that was just one piece. Right? What do you need for the line? Point, slope. So let's go back. They didn't give us the full point. So how could I figure that out? Plug in 6 where? Into the original function, right? If you want to get a y value, don't plug into y prime, plug into the original y, right? So if I plug in 6 to my original function, I'm going to get 8 over square root of 6 minus 2, which is square root of 4, which is 2, and 8 over 2 is 4. So my point is 6, 4. Whew. Everybody on board with that? Where do I get my slope from?
The derivative.
You plug 6 in to the derivative. The derivative is the rate of change. That is the slope. All right?
That's the slope of the function at any value of x.
Yes. So this time we're figuring out what it is at 6. So I'm going to plug in 6 for x in the derivative. 6 minus 2? 4. The 3/2 power means square root it, which is 2, and then cube it, which is 8. Negative 4 over 8 is negative 1/2. Neg action. Do you see where I got the point and the slope from? The point came from y. The slope came from y prime, the derivative. Okay. And so for the tangent line, that would be y minus 4 equals negative half x minus 6. You guys agree? Y minus 4 equals negative half x plus 3. So y equals negative half x plus 7. All right. So what have we done? We had an original function, y equals 8 over the square root of x minus 2, which was not pretty. But I have made the line that is going to graze our function at the point 6,4 at that instant parallel. All right? This is the tangent line at that point. Feel accomplished. There is an alternative formula for the derivative. It's pretty much something we're not going to use. Right? The only place that it would really pop up for me is later on when doing a proof of a certain rule. It would be convenient to use this form. Even then, it's not required. But just so you've been exposed to it and I can say you've seen it. All right? This is the limit as z approaches x, f of z minus f of x over z minus x. Again, it's slope formula, and you're taking the slope as the 2 points approach each other, which is what we saw happen previously. Now, to summarize, f prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. This is our standard definition. F prime of x is the derivative with respect to, which I'm just abbreviating, x. F prime of x is the slope of the curve f, or if I want to, I can call it f of x. So f prime of x represents the slope of f of x, all right, at any point. F prime of x is the slope of the tangent line at x. All right. f prime of x is the, and I'm putting in here, instantaneous rate of change of f of x with respect to x. So that's where those two applications, the rocket and the balloon, fall in. The derivative means all of these things. The derivative, f prime of x, that is the slope of f of x. It's the slope of the tangent line at x. It's the instantaneous rate of change of f with respect to x. Right? It represents all of these things. All right? And again, we had other notations, not just f prime of x. There's dy dx, y prime, df dx, and we can have d dx applied to f. All right? Now, this last one is not one we're actually going to see in terms of we write the derivative this way, but it's good to note that d dx is an operator. Right? Like a plus sign is an operator. What does a plus sign do? It adds. What does a division sign do? It divides. What does d dx do? It does the derivative, which we call differentiates or finds the derivative. All right? So dx is just like a plus sign sitting out there. It has a meaning, but it's incomplete on its own. D dx means derivative with respect to x. Well, derivative of what? Just like a plus sign out there, well, what's being added, right? But that is the operator. The process of finding the derivative is differentiation, or finding the derivative, right? We have fancy $5 words, normal $1 words, and then you have the penny word, right? The prime thingy. All right, so here's the thing. We know a lot of stuff about functions. You spent a great deal of algebra talking about functions. And one of the most important things about a function is that it has a domain. All right? So now, here's the derivative. The derivative is a function. It's a function of x, right? But if the derivative is a function, that means it has a domain. All the wonderful, lovely stuff that applied to functions applies to derivatives because they are functions. All right? So, we know that sometimes functions are not defined, right? So guess what? Sometimes derivatives are not defined. Now, if you have the graph of the derivative, then it's easy. Where are things not defined? Open circle, a jump, or not a jump, asymptote, for example, right? So if you have the equation, it's easy. But what if you don't have the derivative? What if you have the original function itself? All right, so let's talk about differentiability. All right? Differentiability is just a fancy way of saying the derivative exists there. All right? It's in the domain of the derivative. All right? Now, the definition of the derivative is a limit. Later on when I teach you the shortcuts, we hide that. We sweep it under the rug, but it's always there. The definition of the derivative is actually a limit. And when, let me scratch that. What do we have to have for a limit to exist? An approach from the left, an approach from the right, and they have to match. All right? So, the right-hand derivative is the limit as h approaches 0 from the right of f of x plus h minus f of x over h. They're plugging in a for x. The left-hand derivative is limit as h approaches 0 from the left of f of x plus h minus f of x over h. They're using b for x here, putting it on an interval, right? So in order for the limit to exist, the limit from the left and the limit from the right both have to exist. What's important to note here is that we're not talking about the limit of the function. What are we talking about? The limit of the derivative, well, the difference quotient, right? So let's take a look. So when we talk about the derivative, we talk about the slope of the curve. So when I talk about the limits have to match, I'm not talking about the function. I'm talking about the slope, the derivative, right? So let's look at this first example where we have what they very intellectually call a corner. All right? So my graph comes up and then it has a sharp turn. It makes a corner. All right? Now here's the thing. Is the function defined at that corner? Yeah, the point's there, right? Is the derivative defined at that corner? Well, in order to check, we have to see that the slopes from the left and the slopes from the right exist and are the same. Do we get a slope from the left as we approach from the left? Yeah, they show these gray lines as we approach and we reach the tangent line from the left. So here we have the tangent line from the left. It's got a positive slope in this case, right? What if we approach from the right? So again, we have all these secant lines as we approach the tangent line. And when we finally arrive, that limit, the tangent line from the right, gives me a negative slope. So both of them exist, but do they match? So the derivative does not exist where your original function has a corner. Right? And to say that more simply, the function is not differentiable at a corner. Right? Functions are not differentiable at corners. Let's look at the example on the right. So here, this is not a corner. This is a cusp. All right? So imagine if we suddenly shoot straight up and then fall back, right? We leave a cusp behind. All right? Now, here's the thing. At first blush, when I approach the tangent line from the left and I approach the tangent line from the right, it looks like they're matching, right? Only here's the thing. Look at the secant lines as we come in from the left. What are the slopes of those secant lines from the left? They're positive, right? Those are increasing lines, and it's getting more and more steeply increasing as we approach, right? So from the left, the slope is approaching infinity, positive infinity. All right? Meanwhile, as I come in from the right, look at the slopes of these secant lines. What are those slopes? And as I approach the tangent line, they're getting more and more steeply negative. So from the right, we're approaching negative infinity. Those don't match. So the limit for the difference quotient does not exist, and therefore the derivative does not exist at a cusp. So wherever your graph of your original function has a cusp, the derivative will not exist. Or we'd say your function is not differentiable at a cusp.
When you talk about the derivative function of a function, can you graph that?
Yes,
Derivative?
we're gonna do that, Grasshopper. I promise. All right. These are not graphs of the derivative. We're not seeing the graph of the derivative here. We're determining whether it exists or not before we even graph it. There are two more instances. So if we look at the one on the left, this is not a cusp now. If we approach from the left, the slopes of the secant lines are approaching negative infinity. And as we approach from the right, the slopes of the secant line are approaching negative infinity. So actually, this time, they do match. So what is the limit? Negative infinity. But I already told you, negative infinity was a special case of does not exist. And so, nevertheless, we say that a function is not differentiable whenever it has a vertical tangent. All right? Right? What is the slope of this? It's undefined. The slope of a vertical line is undefined. All right? Think back to your algebra. Therefore, the derivative does not exist at that point. Now, does the derivative exist over here at q? Well, that's q minus b, yeah. Over at q plus? The derivative exists everywhere along this graph except at the point P. Right? Now, the next two graphs are both illustrating the same thing. In the middle, we have a jump, and then on the right, we have a removable discontinuity where a point was just dragged out and moved somewhere. All right? So here's the thing. As I approach from the left, right, notice that the approach from the left, the secant lines all have to touch this bottom branch. So from the left, we approach a tangent line that becomes vertical. Right? Now from the right, the point's actually there. These secant lines just approach some value, in this case negative as depicted, right? But do they match? Do the slopes match from the left and the right? Then the derivative does not exist at that point where the jump is. Right? Similarly, if the point is up here, every secant line would have to go through that point, and then some other point down here, we again approach positive infinity from the left and negative infinity from the right. Do the slopes match? Nope. So the derivative does not exist there as well. All right? So there are four things where a function is not differentiable. Four things. Corners, cusps, vertical tangents, and discontinuity. All right? If your original function has a corner, the derivative will not exist. If your original function has a cusp, the derivative will not exist at that point. If the original function has a vertical tangent line, the derivative will not exist at that point. And if your original function has any discontinuity, jump, asymptote, or even a single point missing, right, the derivative will not exist at that point. Is that okay? So I expect you to be able to identify that. Identify those four things on a graph. All right? Cusps, corners, vertical tangents, and discontinuity are all problems for the derivative. All right? Is that okay? Now, that last one. If your function is not continuous at a point, the function is not differentiable at that point. In other words, that last part is equivalent to saying f prime does not exist at x equals c. Same thing. All right? Now, there's something in logic called a contrapositive. All right? So the contrapositive of an if-then statement is when you flip the statement and negate it. And in logic, both have the same value. So if I make a true statement, the contrapositive will also be a true statement. All right? So the contrapositive of this is saying if the function is differentiable at a point, f is continuous at that point. In other words, the existence of a derivative proves, without even seeing the original function itself, that it's continuous at that point. All right? And continuity was important for us because that's what allowed us to use direct substitution for evaluating limits and other wonderful things. All right? So, where is a function not differentiable? In other words, where would a derivative not exist? Corner, cusp, vertical tangent, and discontinuity, right? Then on the flip side, our theorem tells us that differentiability implies continuity. All right? So if I ask you where a function is continuous, all you have to do is give me the domain of the derivative. If it's there, the original is continuous. All right? That makes it nice. Basically, we're simplifying things to questions of domain, because domain you know how to handle. Fingers crossed. Fingers crossed for you guys. I know there was a test question. We'll see. All right. Let's jump into one of the exercises here. So number 31. So what they've given us here is they've given us a function f. All right? Now, you guys tell me, what is the domain of this function? -4 to +6 brackets, right? Where is f differentiable? Well, look for your 4 things. What do we have here? We have a bunch of corners. All right, nobody likes those. So where are my corners? We have a corner at 0. We have a corner at 1. We have a corner at 4. And that's it, right? Also, and your author takes a bit of a weird position here. Endpoints are kind of a weird case. If I look at the end, there's no approach from the left, right, at the far left, and there's no approach from the right at the far right, all right? So, technically speaking, we would say that it's differentiable from -4 to 0, 0 to 1, 1 to 4, and 4 to 6. Is that okay? It's differentiable everywhere but 0, 1, and 4. Is that okay? Now, let us attempt to graph the derivative. So this is what the graph of f prime will look like. Now, what is one of the interpretations for the derivative? Slope. You guys agree? So if I look at my original function, if I know what the slope is, then that is the derivative at that point. Now, this consists of line segments, and nicely, you have a constant slope along a line segment, right? You guys agree? What is the slope along this first line segment?
2.
It's rise over run, isn't it? Rise 2, run 4. 2 over 4 is 1/2. I stumped you with the first slope. What is the slope for this second line segment? -4. You fall 4 and run over 1, right? The slope for this third line segment? 0. And the slope for our final line segment? Rise 4, run 2. 4 over 2 is 2. So these are the slopes. All along that last line segment, the slope is a constant 2. But then there's a jump to a slope of 0 along the next to last line segment, and so on, right? So when I graph my derivative, from -4 to 0, I just have 1/2. It's a flat 1/2 from -4 up to 0 because the slope is staying constant. Does that make sense? What happens at 0? The slope jumps to -4. So from 0 to 1, right, the slope is a constant -4. You guys agree? Then what happens at 1? The slope goes to 0. It makes a jump to 0. So from 1 to 4, your derivative graph is a constant 0. Is that okay? And then at 4, what happens? The slope jumps to 2, and we have a constant 2 out to 6. So this is what the graph of the derivative looks like for that function. All right? You're graphing the slopes, whatever the slopes are on your original. So original graph in blue, derivative graph in red. This is what it looks like. So we have discontinuities on the derivative. What is the domain of your derivative here? -4 to 0, not inclusive. 0 to 1, 1 to 4, and 4 to 6. Right? Differentiability of f, domain of f prime, same thing. Right? It's just that for domain of f prime, you see f prime. For differentiability, you don't have to see f prime, but they're the same thing. How does that? You've now seen what a derivative looks like. All right? Let's look at number 40. Right? Here we're told to show that the function is not differentiable at a specific point. All right? Now, show means more work, right? Hopefully the answer is easy. This is differentiable everywhere except 1. What's wrong at 1? Corner. All right? That's what I expect you to be able to do. Name corner, cusp, vertical tangent, which is the one people always forget, or discontinuity. So we know 1 is the problem. Everywhere else is fine. But how do we actually show it? We have to show the limit as h approaches 0 from the right exists or doesn't exist, right? And this would be f of 1 plus h minus f of 1 all over h. Because it's x equals 1, right? We're at 1. Now, that's the limit as h approaches 0 from the right. What am I using if I'm approaching from the left? Y equals x. So what is f of x plus h? X plus h. And what is f of x? X. And this couldn't possibly be easier. The limit as h approaches 0 from the right, x minus x cancels. H over h is 1. And the limit of a constant is itself. Yeah, let me change that notation. So that was the approach from the left. We need both of them, so that's okay. Thank you. That was the approach from the left. Now let's do the approach from the right, for real this time. So the approach from the right starts out the same. The limit as h approaches 0 from the right of f of 1 plus h minus f of 1 over h. So now we have the limit from the right. So, the actual right, this time, right? What function are we using? 1 over x. So what is f of 1 plus h? Yeah. Technically, these x's up here were 1s. Doesn't matter, it still worked out the same. So 1 over 1 plus h, and then f of 1 is 1 over 1, all over h. So this one doesn't work out quite so nicely, but that's all right. What do I need? LCD is 1 plus h. So 1 minus 1 plus h all over h times 1 plus h. Limit as h approaches 0 from the right. Distribute the negative. 1 minus 1 cancels and leaves you with negative h. Well, that's going to reduce with the h in the bottom. So negative 1 over 1 plus h. All right, once again, this isn't that bad. From direct substitution, we have negative 1 over 1 plus 0, which is negative 1. You guys agree? So the limit from the left and the limit from the right both exist, but unfortunately they do not match. So the limit as h approaches 0, f of 1 plus h minus f of 1 over h does not exist. Right? And that's the definition of the derivative at 1. So the derivative at 1 does not exist. Is that okay? Right? So this would be a little more formally, right? How you'd more formally show that you have not differentiability at a point, right? The derivative not existing at a point. For testing purposes, name them. Corner, cusp, vertical tangent, or discontinuity. All right, I'm going easy on you there.
First part, is that supposed to be 0 or did I miss it?
All right. Let's look at number 46. All right. So here they ask us a couple of things. Where is this function differentiable?
Zero.
That's where it's not differentiable. Why is it not differentiable at 0? Discontinuity. Where else?
-2, -1.
Yeah, the endpoints, they're kind of weird, but we'll throw those in there. What's going on at -1? Corner. What else? What's going on at 2? Discontinuity. You guys on board with that? So that's where it's not continuous. I'm sorry, differentiable. So where is it differentiable? -2 to -1. -1 to 0. 0 to 2. And 2 to 3. So it's differentiable on those intervals. You guys agree? At -1, we have a corner. At 0 and 2, we have discontinuities. And the endpoints are what they are. If we do include special cases, like I said, your author's a little weird about it. He does include the endpoints. That's okay, all right? Just be aware that's not standard for calculus authors across the curriculum, all right? But I guess for his homework purposes, all right, put him in there.
So we do include.
For him, all right? It's something I'm somewhat disgruntled about, but for the homework, yes. All right? Mm-hmm. Technically, if you're on the left endpoint, there is no approach from the left. It shouldn't be differentiable at that point, but he makes an exception for it. All right? And he does it for one particular reason, and I'll point it out when we get to it. All right, so that's where it's differentiable. What about where this function is continuous? Where is this function continuous? -2 to 0, and then 0 to 2, and then 2 to 3. You guys agree? For a function to be continuous, we did that in 2.5, you just need a limit from the left for the function itself, a limit from the right, and the point, and they all match. So, what's the difference between these two? Which of the points didn't fall into both of these categories or out of both of these categories? -1. That corner, we do have continuity there, but we don't have differentiability. So continuity is not strong enough to guarantee the derivative exists. All right? On the flip side, the derivative does guarantee continuity of the function. All right?
But not exclusive.
Correct, it's a one-way street. Differentiability tells you continuity, but continuity does not tell you differentiability. All right? What's the domain of this function? -2 to 3. So these are three different things, right? They're different questions, and they give you different answers, where something is defined, where something is continuous, and where something is differentiable. Now, differentiable is equivalent to saying where f prime is defined. So notice that we're taking this, dropping down a level, and now coming to this on the derivative. All right? All right. I want to finish on a note that's horrible so that we can start next class on a note where I come in my shining armor on my noble white steed and rescue you. All right? Let's let y equal x to the fourth over 4. And I want the derivative. So you guys are going to help me out with this one now. So let's set up the definition. So I'll use the dy dx notation, just so you're familiar with it. dy dx equals, what's the setup? Limit as h approaches 0. Let's go ahead and fill out the difference quotient. That's okay. X plus h to the fourth over 4. Keep on. Minus x to the fourth over 4. All over h. Are you guys okay with the setup? All right. So, do we like the complex fraction? No. Two ways that you can deal with it. One way is to use the LCD. That's fine. Another way is you can pull the fourth out front because you can factor it out and coefficients come along for the ride with limits. So what do you want to do? Okay. So I got 1/4. You really want to just jerk that fraction out of there. Limit as h approaches 0. X plus h to the fourth minus x to the fourth all over h. So we got 1/4 limit as h approaches 0. What now? Binomial expansion for a fourth power, right? Now the good news is there's no numbers inside, so at least all we have to worry about number-wise are the coefficients. Yep. Some of you might know it off the top of your head, but let's just do it anyway. Okay. So second stat, go to my list, ops, and choose sequence. I'm going to do 4 math PRB combination x. That's 4 choose x. X is your variable. You count from 0 to 4 by 1s. And your coefficients are 1, 4, 6, 4, 1. All right? So this means I have 1 x to the fourth plus 4 x cubed h plus 6 x squared h squared plus 4 xh cubed plus 1 h to the fourth. So there's your 1, 4, 6, 4, 1. You have x fourth, x cubed, x squared, x, no x. You have no h squared, h cubed, h to the fourth, right? Now that was all just this component here. So we still have minus x to the fourth, and it's still over h. I need more room, so I'm just going to move. So what goes down at this point? If you were hoping to sate your bloodlust by slashing and burning a lot, it didn't. All right? But it was enough. So I have 1/4. The limit as h approaches 0. And everything that's left has an h in it. So what goes in my parentheses? 4x cubed plus 6x squared h plus 4xh squared plus h cubed. And now we can use direct substitution. So that's 4x cubed plus 0 plus 0 plus 0. And therefore my answer is x cubed. All right? So what is the derivative of x to the 4th over 4? Just x cubed. All right? Now, I've teased you with the shortcuts, and I will lead off with that next time. However, at least one test question requires you to find the derivative using the limit definition. So let's practice using the limit definition, even if some of you guys happen to know some of the shortcuts already, all right? Because you're going to have to do it for the test. And I think it's like 10 points, so don't throw away a letter grade for nothing.